presenter of the first paper, and first of all, let me welcome all of you to the first hybrid ICT-IS 2021 conference, and it's my pleasure to start session Information Systems Technologies and Applications. I wish all of us a fruitful discussion and enjoy the staying here or there. I welcome the first presenter, and the first paper is Automated Software Design for FPGAs on an example of developing a genetic algorithms. The presenter is Tural Mamedov. You're welcome.
Okay, do you see the screen?
Yes.
Yeah. Okay. First of all, good morning, dear listeners. Okay, my name is Tural Mamedov, and I'm presenting the paper with the following topic: automated software design for FPGAs on an example of developing genetic algorithm. And first of all, I'd like to talk about the issue that this paper covers: the rapid growth of integration degree and functional complexity of modern electronic devices results in necessity of improving and developing methods of designing the programming integrated circuits. In particular, field programmable gate arrays, which called FPGAs. And FPGAs contain an array of programmable logic blocks and a hierarchy of reconfigurable interconnects that allow the blocks to be wired together, like many logic gates can be wired in different configurations. And these logic blocks can be configured to perform complex combinational functions or merely simple logic gates. And in most of FPGAs, the logic blocks also include some memory element, which may be simple flip-flop or more complete blocks of memory. And many FPGAs can be reprogrammed to implement different logic functions. So the purpose of this paper is to apply the tools of the automated design of parallel programs for FPGAs in language called VHDL, and illustrate the approach with an example of designing a genetic algorithm used at the training of multi-layer neural network. And also, I will show you the results which we got. And the design of the parallel programs for FPGA being proposed is based on the system of algorithmic algebra, focused on the high-level construction and transformation of algorithms represented in the form of schemes. System of algorithmic algebra is the two-sorted algebra, where you see the example on the screen, where PR and OP are the sets of predicates and operators defined on an information set, and omega is the signature consistent of logic operations like disjunction, conjunction, negotiation, and operator constructs, in particular the serial execution of operations, branching conditions, and for loop. And the representation of algorithms in algebra of algorithms are called SAA schemes. The main difference, in this paper, we used Glushkov's system of algorithm algebra, which actually have a difference with from other procedural programming languages, and the Glushkov SAA allows to specify programs in algebraic and natural linguistic form, and contains facilities for formal program transformation. And actually, algorithms are designed using a list of SAA constructs and a tree, and the user chooses the constructs from the list and adds them to the algorithm tree. And on each step of the construction process, the system allows a user to select only those operations, the insertion of which into the theme does not break its syntactical correctness. Okay, and the next one, the next thing that I want to talk about is VHDL, where high-speed integrated circuits hardware description language. It's like formal notation aims at the description and logic organization of digital system. And the function of the system is defined as the conversion of values at its inputs into the values at outputs. And the organization of the system is defined by a set of connected components. And the language is intended for modeling primarily on a gate level, register transfer level, and chip frames, and is used as synthesis of devices. And also, VHDL has facilities for describing asynchronous parallel process. An entity and an architecture belong to the main context of this language. And here I would like to show you the description of the entity in system of algorithm algebras. You can see an example. And actually, what is the entity? The entity is defined as an interface of the project object, and its description of the project component having well-defined inputs and outputs and performing a certain function. It can represent the whole system being designed, some subsystem, device, node, chipboard, or microcell, logic unit, or something else. Here you can see the example of the entity definition and the example of operators declaring the input and output ports can be used as following. You can see also in this slide. And I will show you in the future how it looks like in real some application. Architecture. The architecture defines the behavior of the system or its structure on a functional level of its description. The description of the architecture in system of algorithm algebra language is the following. You can see it in the screen, in the slide, where arch name is identifier of the architecture. Entity name is the name of the system entity for which is architecture defined. And operator 1 defines architecture declarations, which may typically to be just some type or subtype or signal, constant, file, alias, component, some maybe attribute, function, and so on. And operator 2 are operator that describe the system behavior. And also we have a process in VHDL. The operator of the process belongs to the parallel operations, and it defines the independent sequential behavior of some part of the project, described by an ordered set of sequential operators. The constructor is the following. You can see it in the screens. Also, the name is the identifier, followed by the optional list of signals, and operator is define the process body. Here you can see an example of combinational circuit. We can see how it works in applications. We have 3 inputs, and first 2 inputs are has a logical operator, and we have 1 output. Okay. Actually, this is an example of entity declaration for a combinational circuit implementing a logical function. You can see this. It's the same. This is same thing. So you can also see here the defining the entity for combinational circuit. And here is the definition of architecture, which defining the behavior of above combinational circuit. And also, let's go to the designing of parallel genetic algorithm. We know that evidently one of the main features of neural networks is a parallel processing of signals, and we know that multi-layer neural network are universal parallel computing structures intended for solving various classes of tasks. In implementing neural networks for FPGA, each network layer is working in parallel with others, which allows using the pipeline principle. And neurons in each layer work in parallel too, according to the principle of multiprocessor processing of data. And thus, every neuron is a separate process, and processing information in each neuron is carried out simultaneously. Each neuron is presented as a separated block consisting of several parallel processes, and the neural network is like a multiprocessor system. And this programming language, VHDL, allows to explicitly define signals launching process. Okay. So in this part, we'll talk about a parallel genetic algorithm for training neural networks on FPGA, and the designed in system of algorithm algebras with the further generation of VHDL code. Actually, every neuron corresponds a process in VHDL language. And based on this, the neurons, like a separate processes, are naturally combined into one network. Outputs of the presenting network layer launch the processor of the next layer. So the training of artificial neural network consists in the tuning of weight coefficients of its basis elements, as a result of which the network performs certain tasks as recognition, optimization, approximation, and controlling. So preparation of hardware implementation of neural network training procedures with a genetic algorithm is done based on graph. Here is it. And you can see here how they create their chromosomes and evaluate and run actually through the neural network, checking some check some validation, have some validation process, and so on. Yeah, and I will talk about these here in more about the implementation of genetic algorithm. So we have it consists of these steps. First, of initialization of initial population with chromosomes that contains information about the values of weight coefficients, and a set of chromosomes is represented as two-dimensional array. Then the evaluation of chromosomes of the current population. Each chromosome is decoded to a set of weight coefficients of neural network. The values of fitness function are calculated, and they are take into account then error and network complexity. These function actually define the difference between the obtained network output and the required one. And the third step, if one of the values satisfied the problem's condition, then goes to the step 7. Then selection of chromosomes for further crossover and mutation, application of operators of crossover and mutation selected in the previous step. And the last one, the genetic algorithm is stopped and it obtained values or are substituted into the neural network. Here is a representation of chromosomes population with the two-dimensional array. This is related to the first step. And this is the calculated values in steps 5 and 6. These operators of crossover and mutation. Here is the genetic algorithm block, which consists of the ports which retrieve input signals of the port and save the value to be obtained as a result of training, and the output port which shows the current value of the output after each training iteration. And the signal creates delays in 1 picosecond. Here is the results. So we are considering the example of the training one neuron with 3 inputs and 3 weight coefficients correspondingly. The hardware implementation of genetic algorithm according to the proposed methodology was done in the environment, which you see in the slide, and modeling using ICS simulator. Here you can see in the screenshot the signals, the purpose of finished, for example, the purpose of the finished teaching stores the information the training of the neural network is finished. Start, for example, launch the process, forms the output of the network for each new set of weight coefficients. For example, I is a number of chromosomes on the basis of which weight coefficients were formed before the launch of the process, forming the network output. For example, nodes forming is a set of 2, 1, while the chromosomes are run through the neural network. It transits from 0 to 1 when all 6 chromosomes are processed, and the process can be proceed the results analysis, finish the algorithm, or form new chromosomes using crossover or mutation. Here you can see also the analysis is set to 1 while it will be set to 1 while the information obtained at running chromosomes through neural networks is analyzed. You can see here that the process of adjustment of weight coefficients of a neural network completed in 3 iterations. And actually, I want to show you the comparisons that were made with other works. And the comparisons were made with the highest similarity of parameters and implemented the same chip. And actually, the blue shows the, in the vertical dimension, you can see the training time. In the horizontal is the works. And you can see this not really the works, but the parameters which was used in the works. And you can see here that the results of this action modeling show that the developed method of the training of neural network with the genetic algorithm at hardware implementation of FPGA allows significantly speed up the adaptation of neural network components of control systems, and thus it increased their efficiency. And thank you for your attention. Yeah, if you have any questions, you can ask me.
Thank you, Tural. So please, questions. Everyone is invited to. Yes, please.
Just to clarify the direction of the study, can you hear me?
Yes.
Yeah.
Okay, thank you. Just to make sure. So, are you training a hardware implementation of a neural network with a genetic algorithm? Is that what is done in this work?
Yeah, it's some. Actually, yeah.
So the neurons are hardware neurons.
It's considered to be hardware neurons.
Okay, thank you.
Thank you. Please, other questions? Maybe I have a couple if there are no others so far. So you are training neural network, but few questions about your neural network. What is intended to? So why you are training neural network? What is the architecture of this neural network? On one of your slides, it was declared that it was just one neuron with 3 inputs. So why you are training such network? What do you want to get from it? And on which data are you training your neural network? What is the size of your training set? Do you have a testing set to validate your neural network? And what is the size of your testing set? So this is all about your neural network. Architecture, purpose, training set, and testing set.
Okay, first of all, in those slides that I show the one neural network that was actually an example of how it works. Just to be more simple, I decided to show that only in one neuron. Yeah. So there are actually a lot of them in the work. Secondly,
So what is the purpose? What do you want to get from this neural network?
Actually, the purpose One second. Actually, the purpose is to use the how to say that? One second. And we have different approaches to use the genetic algorithm. It can be actually there can be a lot of things to why we are using the genetic algorithm, but the main idea was that there are a lot of papers, especially if you will look at the paper itself. There are a lot of papers in the references which used some I would say approach to implementation of these genetic algorithms on FPGAs with different approaches. And actually, our purpose was to show that our approach with using the algebraic specifications based on these Glushkov's algorithms will work better than theirs. And actually, about the size.
Yeah, about the data. What was the training set? What was the size of the training set?
Okay, here there actually we are using the sets that are used in the similar works, and here you can see as I show you the experiment results. And here, yeah, it's not shown the size, but for example, in the first 14 work, there were 64 chromosomes, and there were 500 number. 500 is the number of epochs in the genetic algorithms. And for example, in 15 work, it was 16 chromosomes. It and 256 number of epochs in genetic algorithm. In third, it was 20 chromosomes and 380 epochs. And in the last one, there was 32 chromosomes with a epoch number 200, I think.
Okay, thank you. Any other questions? So I do not see questions neither from the chat, neither from nor from persons. So thank you once again, Tural, for interesting presentation. And I invite the presenter of the next paper entitled Latent Representations of Terrain in Aerial Image Classification. And who will be the presenter?
Myself, Serge Dolgek. Just a second.
You are welcome.
Can you see my presentation?
We can see your screen.
Okay.
A browser window, I guess. Yes.
Oh, did I share it correctly? Just a second.
Probably you should share not the entire screen, but an application window.
Yeah, for some reason I don't see this application window, but I'll just share entire screen.
Okay.
And then I'll run application. Is it better now?
Yes.
So good morning, everybody. Thank you for this opportunity to present our work by a research group at the National Aviation University at Kiev, Ukraine. The title is Latent Representations of Terrain in Aerial Image Classification. So the motivation for this study comes from in image classification and recognition with specialized data which comes from aerial image monitoring. As a result of in this task, as we know, image classification is very common task in these days, but in specialized areas like this particular one of terrain monitoring, there may not be sufficiently large data sets for conventional classification. So the objective and motivations for this study is to obtain the data which is available and then study its structure with hope that it will help to understand and improve performance of classification in this specific application. So here are the three main objectives of this study. Classification in the environment with deficit of labels, which is what we have. We have a small data set. We don't have a large data set as is common with millions of training samples or even billions. We want to produce representations of this data set and study their structure with the hope that it will help us to either improve the accuracy of classification with smaller amount of training data, or create a new data for training of future networks. In this slide, we have a description of the data set. These are images obtained in live surveillance from a low-flying plane or UAV, a drone. The images are of land, of terrain in several different areas, and data set is constructed from these images obtained in real live monitoring. Images were manually divided and classified into several common classes, such as fields, water areas like ponds, lakes, different types of roads, built areas like settlements, and other. But I have to outline from the outset that we are not dealing here with the conventional classification for which large experience and many works are available to train a model such as artificial neural network with classified data set and study its performance. This is not what we are doing here. Instead, we are producing a representation, a compressed representation of the data via models which are called generative self-learning models. So we are not using these labels here in the data set for training of a network. We're using them to investigate and understand the structure of a representation that is produced by training artificial neural network of generative self-learning. And now I describe the model in detail in just a few slides. So the model of what we have is a deep convolutional autoencoder neural network. Basically, I'll just skip forward to show high-level diagram for those who are not familiar with that type of architecture. So on the input, on the left-hand side, we have input data. It goes through a set of neural network layers with an objective to compress or reduce the dimensionality of the data. So the latent layer, which is right in the center, usually has the smallest dimension in the network. In dimension means, of course, the size of the layer or the number of neurons in the layer. And then the model is constructed symmetrically. So in the right-hand side, the decoding side, it returns through the similar layers or exactly the same layers to the original shape of the input. So objective of training such a generative self-learning model is to match the input to the output, or to reduce the error from the output between the output produced by the model and the input to the minimum. Such a training process, which is called self-supervised learning, does not require labeled data. So the classes which I showed earlier are not used in training of a network. They are used for something else. So now just to show the implementation of the neural network model, it has two stages. First one is convolutional stage, and this is a pretty standard convolutional architecture with pooling and convolutional layers. The objective of this part is not to produce a compressed representation yet, but to capture high scale features. So to obtain a scaled representation from the entire image and not from specific neuron pixels in the input data set. The decoder architecture is symmetrical, as is common in autoencoders. So not much to be said here, unless there are any questions. And this is the second stage, where an input from the convolutional autoencoder, the first phase, is taken, which is as a numerical array, which is supposed to have in this array encoded some information about the image, not only particular to specific pixels, but also some scale features of the image. And that numerical array is then sent to a common deep autoencoder with the objective to reduce dimensionality. So on the output, we should obtain a numerical vector of the same dimensionality as the input. And the training, which I'm gonna talk about a bit later, training is intended to reduce the error, the cost function measured by cost function between the input and the output sets. As a result of training, we produce latent representation. Latent representation is the output of a latent layer of a trained model. The output, it means activations of all neurons in the latent layer, and basically the activation of a neuron corresponds to a coordinate in a representation space. So these are some slides on training. As I said, it's pretty standard. There is nothing specific in this study about the training. These normal gradient descent type algorithms, the model is trained until plateau is reached in the value of cost function. So as a result of training, we obtain a latent representation of a data set. Essentially, what happens is if a set of images, 10,000 of them or so, is compressed to an array of the same number of samples, 10,000, but with dimensionality of 3. So we can observe the compressed representation of this data set of images in a three-dimensional representation space. And some characteristics of this representation can be measured without any labeled sample. So that includes the size of the data set, the variation in each coordinate, a density distribution in the representation space. We also, one of the objectives of the study was to understand how the concepts which are classes or concepts which are of interest to us are represented in the latent space. Are they compact or large, for example? How do we compare it to the size of overall data set? Do we overlap a lot, or are we separated? So these are important questions for learning, because understanding the structure of data in the compressed and formative representation can be essential for effective learning with smaller data. So these distributions show us the example of some classes. Classes are in the left-hand column. Narrow roads are green. Footpaths, different types of roads here. And we can see that for each class, a representation region of this data type or concept are sufficiently compact. So we are not spread through the entire representation latent region where all data points are located, but it's more to gravitate toward a specific region or area in the latent space. Here in the next set of slides, we show the separation between different concepts. Again, it can be seen that some concepts or classes, I use them interchangeably, show very good separation. So their overlapping region is very small. And this is important for some of applications because having trained for a number of applications, probably beyond the scope of this presentation, but this is an interesting and important result which shows that some concepts are well separated in the latent representation. This observation did not apply to all concepts, and this is understandable because what we are talking here in this study, we do not use labeled data for training at all. So the structure which is created as a result of training is entirely unsupervised. So it's a natural representation of a data set which does not have any knowledge about high-level concepts. And because of that, there is no guarantee or even expectations that there will be one-to-one strong correlation between our high-level concepts, which we impose on the data, and the internal distribution of this data. However, as we can see for some concepts, it holds very well true. So it could be expected that our high-level concepts do have a strong correlation to some natural structures in the latent representation of the data set. So why is this understanding structure and detecting it and developing methods of detecting it can be important? One application could be in data generation. Suppose we have seen or have obtained, produced a well-structured representation, by which I mean, by this I mean the concept regions, class regions are well separated in the latent representation space. So in training, as I will remind, maybe I don't want to scroll to the definition of the autoencoder model, but maybe you will recall that there are two stages, the encoding and the decoding. And as a result of training each of these sub-neural networks, each of these components of the overall neural network are trained. That is, their weights and parameters are defined as a result of training, so that the error on the training data set is minimized. So as a result of training, we produce both latent representation in the latent space and two functions, the encoder function from the observable space to the latent space, and the generator function from the latent space back to the observable space. So now, if we have a well-structured representation in the latent space and trained generator function as a result of after self-supervised training, the natural use of this result of this product is to try to generate new data by taking data points in the latent region associated with certain class and forwarding them through the generator function to the observable space. This way, we can obtain a number of samples from the latent space in the observable space, which we can expect to be related or similar to the concept of interest, to the class of interest. That is, we should be able to augment our data sets with more data. Of course, it depends on the quality of training and a number of essential parameters, but this is the idea behind this direction of research. And this is still, work in progress. We do not have more results on a large volume of results in this area yet. Maybe it will be the subject of the next study, but this is an interesting area of application. And what we see is for the classes with very good representation, structured representation in the data set, we obtain reasonably good results of generation. So these are some examples. So to summarize this, the results in this work, so what was shown is that models of generative self-learning were successful in producing well-structured representations of real-world data. This is important here because many results previously were reporting structured representations for simple data or artificially produced data, such as geometrical shapes, for example. But this is real data, not changed in any way, and the fact that the models are still successful in producing some structure, which is correlated with higher level concept, is interesting. We developed methods of measuring and identifying representations in the latent space, the representation regions in the latent space for concepts which are both classified as supervised, which is use labeled concepts, and unsupervised as well. I didn't tell much about this unsupervised direction here because the time is limited for this presentation, but a number of methods have been used to identify the structure in the representation space without any class data. And also, we are starting to see again, just to remind that this is work in progress still. That models can be used for generation of your data, and some preliminary results are promising in this area. So here are some references, and I think this completes your presentation. So thank you for your attention, and if there are any questions, I will be glad to answer them.
Thank you, Serge. Please, the questions are welcome. Maybe so far I have small questions or maybe even clarification. When you were speaking about your data set, training data set, it seems to be imbalanced a bit. Say, for example, we have very few images with footpaths. Um, does it affect the training efficiency, the training accuracy, or maybe you have in some way balanced your data set?
You are absolutely correct. Of course, the data set for efficient training, it has to be balanced. And what we see is the best result we see here is for the concepts or classes with good representation in the dataset, with strong representation of the dataset. This is where the models of generative training were able to identify the concept regions, latent regions, the best. For smaller parts, we just have to. This is another part of the study which is ongoing. Is our data set is supposed to represent the reality, and so we want to understand not only the concepts which are well represented, but also those ones with the poorer representations, and to see how their characteristics are affected by this lower representation. Because again, in the real world, the situation is different. We cannot guarantee what we will see exact same number of one class as that of the other. But this is an interesting question. I have to reiterate that the best results indeed we see with the data which has strong representation in the data set.
Yeah, sure. And you are right as well, because if we will later generate a lot of, say, for example, footpaths, so it will be not very similar to the reality. Okay. So maybe other questions? Okay. No, and maybe you have talked about it, but future work, what will be the next steps in your research?
The generation project is ongoing at this time, and the question you asked is very relevant in this respect. We want to understand how well generation works, not only for main classes, call them principal concepts, but also for the secondary and the concepts with smaller representation in the data set. But there are also interesting directions in theoretical research. They relate more to generality and evolution of learning models. How can models evolve to be successful in learning more complex data? So those are two, the practical and more theoretical and far-reaching directions.
Okay, thank you. Any other questions? I guess no. So I thank you once again for interesting presentation, interesting project. And I invite the next presenter, the paper, Development of Multi-Agent System for Control Autonomous Robot. And the presenter is Matvey Ushakov. You are welcome.
Greetings, everyone. So, 1 second. Can you see my presentation?
Yes, we can see your presentation.
Okay. So my name is again Matvey Ushakov, and we are with Natalia Aksak and Mykola Koroblев. We are all from Kharkiv National University of Radio Electronics, and our topic is the development of a multi-agent system for controlling and autonomous robots. Content of this presentation is introduction, including motivation, analysis of related works and the aim of the work, organizational model of multi-agent system for control autonomous robots, search algorithm based on negotiations, and one second, and simulation of a multi-agent system for control autonomous robots, and conclusions. So motivation is currently large companies join stock companies merged into several companies tend to have central warehouses where the products arrive for storing for a certain time. Any warehouse is faced with the problem of warehousing and cargo handling. Symptoms of errors in managing warehouse process are lack of space, ineffective use of equipment and technical resources, high costs of storage, and handling of goods, poor quality for customer service. One of the tasks to increase the efficiency of the warehouse is to improve the organization of process and technology for performing work. The solution of technical problems includes the development of algorithms for the effective placement of goods at storage locations, movement of goods in the warehouse, picking roads. To solve the problem of internal transportation movement of goods in warehouse, a multi-engine system control for autopilot transport robots in warehouses premises is proposed, which will increase the efficiency of using the warehouse space without equipment, downtime, and queues. Warehouse topic, as well as mobile robots controls, one of the most promising topics. On this slide, you can see all the papers we used in this work. Aims and tasks of the work. The aim of the work is to develop a multi-agent control system for autopilot transport robots to solve the problem of transporting goods in warehouses, which is capable of searching. To achieve this goal, the following tasks have to be solved: is to develop an organizational model of the mobile robots control process, its components, and their interaction. Organizational model of a multi-agent system for control autonomous robots. On this slide, you can see which system we has used. We use the MES system, multi-agent system, and it contains the set of agents, virtual world of warehouse, and connections between agents and the environment. To ensure distributed cooperation between agents, an organizational model is proposed, consisting of the following components. You can see on this figure. A set of a fixed number of agents that determines the composition of the group. System structure describing the relationship between group members and their interactions. States of agents include functions and scope of work performed by agents, as well as sets of allowed states. Awareness of agents, information from external and internal parameters. For the most efficient distribution of work, engines must interact with each other through negotiations. During the negotiation process, the most suitable performer for each job is identified. The negotiation process in the distribution of work consists of the following components: the negotiation object and the negotiation protocol, a set of rules according to which the agents interact. The negotiation protocol is shown on figure 2. Okay. The experiments were conducted on Intel Core i3, 3.9 GHz OS, Microsoft Windows 10, Unity 3D, and C Sharp. When the application starts, the scene is load, on which the map is initialized, figure 3. The agents of the afterport warehouse robots and the station are created. The location of the robots is defined in a random way. The agents that was created on station corresponds to the agent initiator, which distributes the work to other agents. The agents executors are created for each warehouse robot communication with the initiator and receive the assignment from it. On figure 4, it is shown that one of warehouse robots is doing job and the others in standby mode. Table 1 on this slide it shows the number of steps from the robot to the load, the search range, the time to build the road, and the number of deadlocks that have arisen. It's when the robots are at the same distance to an object. Both with the use of the agent negotiation mechanism for the wave and the A algorithm, and without it. This is shown in this table, solving the problem of transportation along given coordinates using the mechanism of agency negotiations is carried out faster with a smaller search range and without the occurrence of deadlocks. Conclusion. A control system for deploy transport robots in warehouses has been developed to solve the problem of transportation, loading, and unloading of the goods. The system is implemented on the basis of an organizational model of the mobile robots control process using a multi-agent approach. The proposed model describes the interaction of agents, the functions, and the amount of work they perform, as well as the set of admissible states. The implemented algorithm for finding the shortest path in the virtual world of a warehouse to find needed targets. The developed system effectiveness has been demonstrated using computer simulations. Thank you for watching. If there are any questions, feel free to ask.
Thank you for the presentation. Please, yes, please.
Good morning, everyone. I'm Vladimir Malav, sitting here physically in the conference room. I have a question about the negotiation protocol and the role of negotiation in your experimental setting. Could you just return back to the slide displaying the negotiation protocol? Yeah, no. The next one. This is an organizational structure.
Sorry.
You mentioned that the negotiation protocol is a set of rules which are pictured in Figure 2. I do not see any rule in Figure 2. Could you please elaborate on that?
Okay. It works like if we have a robot and we have this sorry. Okay, so to say if we have a robot standing in one place and the target he is moving to, it's working like the grid pattern. So it went makes a warehouse like in grid, and each robot to this place is going to taking its time to coordinates the fastest and easiest path to the target. So it's like if we have maybe 5 grids to the one robot have 5 grids and other have 6 grids, this system will take the 5 grids pass, and this robot which calculated 5 grids pass will going to take the task of transporting this target.
This is not very clear because it did not explain the roles of the agents on the lines of your figure 2. Who negotiates with whom? Which role to which role?
Sorry, can you repeat this? I cannot hear you clearly.
In what you explained, I didn't see any negotiation. It was just an assignment of the work to an agent by the centralized utility, by the coordinator, based on the distance between an agent and the load. What is negotiated and why do the agents negotiate? I do not understand from your explanation.
So it's take me a second. It's I didn't wake up already. So
To pick up,
the robots that we use in will be in the system are going to negotiate with each other. So if one have the easiest path to land, this robot will take the priority. So if they're going to how to say, they're going to negotiate with each other, and then the robot with the easiest path will be taken.
again, what is the objective for their negotiation? Why do an agent engage a different agent in a negotiation encounter?
No, to take the fastest path.
Okay, and could you please return back to your organizational diagram then? Why do you have a centralized organization in the utility like coordinator here? What is the role of coordinator? What does a coordinator do?
Coordinator will coordinate the robots between each other, and it will maybe I didn't say correct when I said that the robots will compute the path. It will be doing on the cloud, and then when it will be computed, then coordinator will take it to the robots that have the easiest path to go.
So you have the system with the centralized control of robots, is that?
Yes.
So it's not a distributed coordination; it's a centralized coordination.
But it will be working on the different, not different, but many robots. It will be not working on one robot maybe.
Well, I don't really care about the number of robots. I'm caring about who dictates the path, the route for any robot in your organization. The coordinator.
Yes.
Then it's centralized control, and you have the system with the centralized control. Going back to my previous question, in this setting, I do not see any need for any negotiation.
Maybe you
If
have a point.
If a coordinator uses the cloud to compute the path, the optimal path for a robot, and assigns a robot with the better position to perform the task, and gives the path to this robot, then the robots just do the work without any negotiation with the other robots.
Maybe you have a point, but we did it like that.
Okay, thank you.
Okay, thank you for the discussion. Any other questions, please? And
If you please allow me, I have a question about the experiment, if I may. Did I understand you correctly? And please correct me if I'm mistaken. That your experiment is simulation in the synthetic setting. So this virtual scene that is displayed in Figure 3 is just simulated. Did you try to perform any real experiments in the uncontrolled environment?
No, we haven't, because we have not signed with any warehouses to do that for now. But maybe in future we will do that and make the real simulation, a real warehouse. But for now, we did it like that.
Okay, thank you for that. And perhaps my final question: how well does your system scale?
Uh,
Did you check the scalability in your synthetic experiment? How many agents did you try?
We tried on our setup. We tried up to 5 engines, but when we started to make more agents, it wasn't enough of our computing power to make it work fast on our computers. So we ended on 5 robots.
That's very strange, because you said that the coordinator does its work using the cloud. Does it use a cloud server and Amazon or something
No,
like
we
that?
didn't. We did it on locally.
Okay, then why saying about the cloud?
It can be run on the cloud, but we run on the local stuff.
So you didn't check it on the cloud?
But cloud, it not really needs to be Amazon or the Google setup. It can be run on the local computer, and then it can be transformed on the cloud.
Okay. Okay. What do you think is a typical configuration of a warehouse? How many robots are in there in a typical company?
It scales with warehouses. Is when the warehouse is small, maybe 5 or 10, but when the warehouse is pretty big, it can be up to 100 maybe.
Up to 100. That was expecting to hear. So you have to experiment with more agents and add more computing powers out there. Or you may wish to switch to a real distributed setting when you do not have a centralized coordinator role in your organization. Did you think about that?
Yes, but we haven't got a lot of time to make it work.
Okay. Okay. Thank you very much.
Thank you once again. Please, other questions? And maybe I have one question or clarification. You are dealing with a navigation inside building. Have you considered how your robots will perform a positioning task inside building?
Yes. So position, as I said, it works like in grid pattern. So as you can see on figure 4, there are shelves with goods on them, and they occupied pattern grids in the pattern. So the robot will be in one grid, and then the shells in the other grid that cannot
Sure,
be.
but how your robot will determine in which grid it is?
We are using easy coordination system, so it will be
Not a coordination system. How to determine the coordinate inside the building?
by cameras and
So you use optical cameras and some markers or something like that?
it's one or another. It will be on the moving position is that they have the trace of where they standing.
Okay.
So they start up from one point, and when they moving from it, it will compute the placement, and it will be shown in system.
Yes, but when powering on, you need at least to determine the starting point where you are. So you rely on optical sensors. Do I understand well?
Yes.
Okay, thank you. Maybe other questions? If no, I would like to thank you for your presentation. I would like to thank for all the presenters who make the presentations during this section. And for my some regret, but the section is over. All the papers have been presented, and we have time for at least virtually coffee break. Thank you, and hope to see you at the next sessions.